Hello, this is the eighth lecture in the series of lectures on tribology for the beginners. Today we'll be discussing the topic of where. Now, where is a very commonly known term, and it is our experience for almost everyone that everything that we see wears out. And the common terminology is wear and tear. But that is wrong because the broader definition of wear includes tearing. Tearing at the surfaces between the two surfaces, the interface, is included in the definition of wear. So we know that we cannot stop wear completely, but it is important to recognize the type of wear and where and how it wears, and to design the machine or machine parts for a known life so that we can replace it after a known life. So this is where the starting point of wear is. Now, there are two terms we have been using in this lecture, friction and wear. Both are loss outputs in the industry, and in any component or any part that we use every day. And friction is the loss of energy, and wear is the loss of material. So both of these are detrimental to our industry and elsewhere. So as we said earlier, that we should recognize it and try to stop as much as possible. So if we want to give a definition for wear, we say that it's a progressive loss of substance or material from the operating surface of a body occurring as a result of relative motion at the surface. This means that we are sliding two components together, one against another, and at the interface, there will be loss of material due to rubbing. And this is what wear is. So this relative motion is a very important phrase in this definition. Wear is a very complicated process, and almost every day we are trying to find out the new parameters that affect the wear process. But to say the few parameters that are well known are load, speed, lubricant, atmosphere. Atmosphere may be the ordinary atmosphere, or salty atmosphere, or inert atmosphere. All kinds of atmosphere is possible, and they will affect the wear process. Material, type of material, whether it is ductile, brittle, or whatever, the surface roughness, smooth or rough surface, contamination on the surface, whether it is an oxide layer there or some other layer is there, these factors will affect wear. So this is our starting point of wear study. Then we go to the next topic, that what are the stages of wear. Now, when the two components rub against each other, or a machine part, machine parts are running, there are usually three stages. And the first stage is called running in, and second stage is called steady state, and the third stage is called seizure or accelerated wear process. Now, running in is also a very well-known phenomena, because in the initial period of any new machines, the machine components are newly machined and they are not smooth. And because they are not smooth, their load capacity is not to the required level. So as it runs, the surfaces become smoother and smoother, and eventually the optimum load capacity is obtained, and then we must stop the running in, or usually some lubricant is used so that the smoothing does not go further. The picture below this shows that a rough surface becomes smoother and smoother, and eventually it becomes very smooth. But we should not allow the surface to be very smooth. If it does, then there is a possibility of seizure, and this we do not allow. So if you want to look at it little mathematically, we assume the where as a function z here as a function of time. Very conveniently, we write it as 2at to the power half, a being a constant. Now, if we derive the where function dz by dt with time, by doing this, we'll get dz by 2t. That means with time, it is decreasing. So this is a decelerating process. And this is quite clear because we see that the slope of the curve is slowly coming down. And this is why it is a decelerating process. So this is also very clear from this picture that it is being smoother and smoother, and wear is coming down. So this is a wonderful way of expressing the running in process by a function of where, by taking the where z as a function of time and differentiating it. So this says that the running in is a decelerating process. So once that is completed, then we go to the next stage, which is a steady state wear. That is second stage. Now this is a stage where machine parts wear in a very constant rate. It wears, but very constant rate and small amount. So here we can represent the wear z again as a function of t as beta time beta as a function of t. So if we differentiate this, then we get dz by dt as beta. Beta is a constant. So this means that here the wear takes place in a very steady manner, and this is usually known as the useful life of the component. So the time between the running in and the accelerated or severe wear is the useful life of the component. Then we have the severe wear, as it can be seen that the wear rate is increasing in a very high rate, and this may lead to seizure, and the component may be unusable. So there we can define z, that is the wear, as a function of t, as c times e to the power gamma t. Now c is a constant, and if we define and if we derive z if we derive z with respect to t again, so dz by dt becomes gamma times zt. That means it's an accelerating process. So it wears out in a very high rate, and it can be seen here in this graph that the wear is accelerated manner. And here it is necessary to erase the wear by some means or other, otherwise the component will be unusable. It is important to remember that both these zone, the running in zone is a decelerating process, but at the end of the decelerating process again, this deceleration should be maintained. And this is what is done in the industry or elsewhere by changing the oil, because during running in, a lot of wear debris are formed, and unless the oil is changed, those wear debris will be wearing the surfaces more and more. And this is why a newly bought machine or car, it is advised that beyond a certain time of run or mileage, we change the oil. This is because of this. The wear debris is harmful, and they should be changed so that new oil will erase the process of wear. So this is the 3 stages of wear, and then we go to important topic, wear law. Now, there are not many established wear laws except Professor Archard's wear law, which has been formulated sometime in 1940s or 50s, and it's still very useful for initial calculation for machine design. Now, there are many variations and improvement and addition to this wear law. Say, for example, writing the wear law to take care of the roughness, to take care of the atmosphere and all that. But the basic wear law remains the same since Professor Archard wrote this sometimes in 1950s. So this says that the V, which is the wear volume, is equal to K. K is a constant, and just like we have got friction coefficient, we have got also wear coefficient. So K is the wear coefficient, and then W is the load, and X is the sliding distance, and PM divided by PM. PM is the hardness. Now, this does not require much thinking, because it's a common experience that if you say, take a chalk and draw a line on the blackboard, the harder you press the chalk, more it will wear out. This is our common experience. So V is proportional to W. There's no problem in that. Longer the line, the more it will wear. So it is proportional to X, that is the sliding distance, how far it has slid. And if the chalk is harder, it will wear less. If the chalk is softer, it will wear more. So it is inversely proportional to PM or hardness. So this is a very simple observation. Professor Archard put it in a wonderful way as wear law, and we still use it for our initial approximation of wear of components in design. Now, this wear coefficient is the important thing here. Just as I say, just as we have got friction coefficient, we also have the wear coefficient. And the whole thing, the law depends on the estimation of this K. So this has to be found out experimentally. And we have got many data. So I have given some selected data. For example, gold against gold, coefficient of friction is very high because they're very ductile and soft. And wear coefficient is also high. 0.1 to 1 is actually high coefficient because usually the coefficient of wear goes in 10 to the minus 8, minus 7, minus 5. So this is a high wear, high coefficient friction. Then again, go down to little more ductile and less ductile copper against copper. And then we have got friction reducing and wear also reducing. And then steel against steel, friction reducing, wear is also reducing. And like that, if you see that harder the metal or harder the rubbing components, the wear is less. Or harder or stiffer, I think, is the right word. Say, for example, tungsten carbide against tungsten carbide. It is only 0.35 is the coefficient of friction, and wear is 10 to the minus 6. Now, polymers usually wear very less. So you can see it is only 10 to the minus 8 to minus 7. So this is a small chart of coefficient of friction and coefficient of wear comparison and gives us some idea of what the broad values are. But there are more details available in the literature. So then we go to the measurement. Now, friction and wear measurement is a very important thing. And those values that I have quoted actually comes from this kind of experimental methods. Now, I have chosen, there are many experimental machinery available. One of the simplest is pin-on-disc apparatus. This is a simple machine. This is a disc mounted on a shaft, and that is rotated by a motor. And this disc rotates. And there's a pin here which is loaded onto it. And as it rotates, as the disc rotates, the pin wears depending on which one is harder. If we take a softer pin and harder disc, then the pin will wear. The pin is loaded by a fulcrum mechanism like this, and a simple way of loading this is shown here. Now, to measure the friction and wear, we put a LVDT in the tangential direction so that it can measure the force that is required to overcome the friction. So LVDT is very well-known sensor, and it is used here. LVDT is used for measurement of wear, not friction. Friction will be measured by load cell, of course. So this is a load cell that is put in a tangential form direction so that it measures the force that is required to overcome the friction. And LVDT gives how much the pin has dropped, or how much pin has dropped. That will give you a measure of wear. So it is a linear variable displacement transducer. So this is LVDT. LVDT gives you wear, and the load cell gives you the friction. There is another very important parameter that is usually measured, and that is the contact temperature. As it wears, very high temperatures are generated here at the contact between the pin and the disc. And this contact temperature can be measured using an infrared camera. But infrared camera, of course, cannot measure the radiation, infrared radiation, unless the pin is transparent to infrared. And this is why sometimes sapphire or other materials are used. Our next slide will show that. This is the machine that we used. This is the machinery we used. Here we used a sapphire pin. And other things are, as usual, we have a infrared camera here with the IR path filter, and LVDT and load cell are, as we described before, and they are measured in different monitoring machines. So this is the one we used in our experiment in 1996, the paper mentioned below. So remember that if we want to measure the contact temperature, our pin has to be sapphire. But then the question arises here that if the pin is sapphire, how do we measure the contact temperature between other type of material? Actually, there are methods of doing it by comparing the material parameters of sapphire and other metals. And this will give us a comparative value. So since we cannot measure the infrared of ordinary material, we measure the under the same condition of load and speed using a sapphire pin, and then convert it to other metal by using a multiplying factor. Okay, so then this gives us a very brief outlook of how we measure at least three of the basic parameters in our tribological equipment, that is friction, wear, and contact temperature. Of course, there are other machineries which can measure other things. For example, if we want to change the atmosphere, then we must do the experiment in a vacuum with different atmosphere created within the vacuum. But those are different type of equipments available. And we won't go into the details of that. So we'll go to the next topic. So having discussed the measurement of main parameters, we go to the types of wear. Now, frankly speaking, when we wear, or when two surfaces are slid one against another, no particular type of wear takes place at a time. There are often a combined form of wear. And we have to recognize what is the most predominant type of wear and try to arrange for its remedy. So we say that although there are different types of wear, but no particular type of wear will take place at a contact. It's often combined type of wear, and we have to take care of the most prominent wear and try to remedy it. So the first one we talk about is the adhesive wear. Now, a little bit of this we have discussed earlier when we talked about adhesive friction. Following Bogdan-Tabor's theory of friction and wear, they propose that when two surfaces are slid one against another, usually the contact takes place at the peaks of the asperities, and since the load is taken only by very few points with small contact area, the contact pressure is very high. And since the contact pressure is very high, there is likely to be plastic deformation, and we call it solid state welding. They get usually welded at these points. And the force required to break those bonds are known as friction. And when we do this, when we move, say, body 1 against body 2, then depending on whichever is softer will be worn away. That means a part of the chunk of the material will be adhered to the harder one, and that will be knocked off by the oncoming asperity next. This is the sequence. So first, a small piece of material is stuck to the top surface, and then as this moves, it is broken away by the oncoming asperity, and it becomes a debris. Now this wet debris may be detrimental for further wear, because they will be wearing the surface more and more as a three-body wear. So in many cases, we call it three-body wear, two-body and three-body wear. So if the wear is only by the asperity welding and subsequent formation of a wear debris, then it is two-body. And if the wear debris itself, debris is formed this way, they wear the surfaces more and more, then we call it three-body wear. So the effect is that we have to somehow eliminate the wear debris, and there are processes of doing it. We'll discuss it as and when it comes. So then how do we prevent it? As we said earlier, that wear cannot be prevented totally. So we try to find out the most prominent type of wear. If we say that in certain case, adhesive wear is most prominent, then we use lubricants and additives. I think the scuffing of gear is probably well known. And if scuffing of gears or cams occurs, this occurs because of the very concentrated contact and very high contact pressure. Then this is usually adhesive. Then we have to use lubricant with some particular additives. We'll come to that. But in some cases, gears may be pitting. This pitting is not an adhesive wear. Pitting is a fatigue wear. So we must distinguish between scuffing and pitting. So if we say in certain case scuffing is more important, then we use lubricants with EP additives. Now EP additives in common terms means extreme pressure additive. Now extreme pressure additive actually means that when the pressure is very high, then we need to put a lubricant that takes care of the problem that happens there. Actually, EP means extreme pressure, but that gives rise to extreme temperature. So the EP additives usually are additives. Those allow the lubricant to be active till high temperature. Usually chloride, sulfide are used, which are formed at high temperature, say 200 degrees centigrade, and they will last till 1000 degrees centigrade or more. So EP additives actually means extreme temperature additives, and they will take care of the components for high temperatures. And these are used for gears and cams and other things. And many newer types of oils are coming up, and much more research is going on, but this is a basic theory that EP additives must be used when there is a contact of very high pressure contact, like gears, cams, and all that. Now, we go to adhesive wear. We go to abrasive wear. Now, abrasive, again, we have discussed abrasive friction. Abrasive friction is basically hard asperities of one surface digs into the soft surface of the other body and plows out material. This is why sometimes it is called plowing wear also, and plowing friction also. So as it plows out, some material will be produced, and they will be produced in a as a wear debris, and they will look something like this. Now here again, as we were talking about two body and three body, if it is simply one hard asperity rubbing against a soft metal, then it is a two body abrasion. But if there are two surfaces and hard asperities are trapped between the two, then it is a three body abrasion. Now, a lot of discussion has been carried out by Starkwick and Batchelor in their book, and we can see that three body abrasion can be also very dangerous at times. So the best way to avoid three body is to eliminate the wear debris. So as we were discussing, for two body abrasion, the only thing we can do is to make the harder surface smooth so that the asperities cannot dig in much more. And see, it depends on the use. This is not in the hand of the user. Sometimes we may have to have a rubbing surface of steel against copper. And this may not be in our control or designer's control. So there we make the steel surface as smoother as possible, because we cannot change the ductility of the opposing surface, copper. So that way we can eliminate abrasion, two-body abrasion quite a bit. But three-body abrasion must be taken care of by filtration. Otherwise, there is no other way. The trapped debris will keep on wearing the surfaces. Okay. Now this is another very important type of wear, which is a fatigue wear. Now fatigue wear, as we all know, is due to the fluctuating load at the that initiates and propagates crack. So it is basically the crack propagation at the interface that produces fatigue wear. Now, to understand crack propagation, we must understand the stress distribution. Usually, if you take a curved body pressed onto a flat, semi-infinite body like this, then there will be a contact surface generated like this. So the contact surface is 2A, and the maximum pressure is P0. So the contact is here, and we have a flat surface made. The curved surface becomes flat at the contact zone, and then there is a pressure stress distribution. Now the figure A gives you the stress distribution. If you look at it carefully, this is the stress distribution in the r theta coordinate. And if we look at it carefully, we can see that the shear stress, tau r theta, shown here, is maximum. The x-axis is A by P naught. Sigma by P naught. Sigma is the stress, and P naught is the maximum pressure. And y-axis is the A by Z. That means they are non-dimensionalized stress against non-dimensionalized depth. So the non-dimensional stress is 0.31 and non-dimensional depth is 0.47. At this point, shear stress is maximum. And usually, the point where the shear stress is maximum, the crack may be initiated and it will start propagate. As the crack starts propagate, the direction of crack propagation is again a very complicated process. But if the crack propagates in such a way that it brings out a small piece of material out of it, then we have got a fatigue wear. So the fatigue wear is due to the stress distribution at the contact. And if we consider an asperity to be a semicircular or semi-hemispherical body making contact with a flat surface of the opposing flat surface, then this is the stress distribution that will work, and the maximum stress which will occur in this case at 0.3 at 0.47 depth and somewhere below the surface and the subsurface, and from there the crack will propagate, and it may take out a chunk of material out of it. As I say, crack propagation is again a very complicated topic, and how and where it will propagate can be theoretically and experimentally determined, and a lot of research going on. But if the crack produces a small chunk of material, then that becomes a fatigue wear. So we say that the fatigue wear in briefly, fatigue wear is due to the fluctuating stress loading and the stress distribution at the contact. In the at the point of maximum shear stress, the cracks are formed and propagate, and that may lead to a small chunk of material coming out. So then, what is the way to prevent it? The easiest way of preventing this is to stop the fluctuating load, but that may not be possible all the time because fluctuating loads are the part of the design system. So there we choose a material in such a way that their endurance limit is fairly low, so that the stress that is produced at the contact may not affect the fatigue process. So the only way to get rid of fatigue wear is to choose material in such a way that the endurance limit is low. We may also have some coating. There are all different kinds of coatings available, and this coating will, of course, help. We may also think of roughness, because roughness will also decide to some extent the stress distribution at the peak of the asperity. So these are the few points that we may consider, but mainly the coating and the material choice are the important ones. But as I say, these are all very important topics and topics of research, and much work is going on. Here we are considering only a very simplified version of the topic. Now this is erosive wear. Now I think this is known to many of us that when there is a two-phase flow means a fluid flow containing solid particles, say air with sand particles, water with again sand or other particles. When they go and hit a surface, some material will be displaced and they becomes wear debris. So obviously here the particle size, particle velocity, angle of attack or angle of impact, and relative hardness of the impacting surfaces are important. There are usually two types of erosion. One is abrasive erosion. Abrasive erosion usually takes place when the surface is almost parallel. We'll see that later on. So that the particle goes and hits the surface almost parallel and takes some chunk out. And impregnated surface erosion, here the particle goes and hits the surface and impregnates and takes out some material out of it. So these are the very broad classification of abrasive and impregnated erosion. But then there are many details available, but I'm giving only one detail. That is, if the angle is only 30 degrees for tough materials, then the maximum wear occurs at an impact angle of 30 degrees. For hard and brittle materials, this occurs at an impact angle of 90 degrees. So hard and brittle material will give impregnated erosion, whereas the, the tough material will have very close to abrasive erosion. So we see that more in this picture, the wear erosion mechanism. Here, depending on the shape, size, and the hardness of the eroding particle, the impact angle and the other two-phase flow parameters, the mechanism will vary. If we look at the first picture here the impact angle is low, and since the impact angle is low, the particle is coming and hitting the surface and taking some chunk of material out, like this, as you can see. So this is an abrasive erosion. But if the particle comes and hits almost vertical, then what it does is it produces a different type of stress distribution at the contact, and it produces cracks, and we may have a fatigue failure. As we have discussed just in the last slide, that the fatigue failure is due to repetitive or fluctuating stress. Obviously, one after another particle hitting the surface will produce a fluctuating load, and that will cause fatigue failure. Then we have high impact angle. Impact angle is high, is almost vertical, and the velocity is medium. Then there will be something like plastic deformation here, and the plastically deformed portion hit by another particle will produce a flake. So plastic deformation, if the impact angle is high and the impact velocity is medium. So if the impact plastic deformation for the ductile materials and for brittle materials, this will produce crack. So with a high impact angle, medium impact velocity, it will be plastic deformation for ductile material and brittle fracture for brittle material. There's another type of wear that we discuss here, is if the particle velocity speed is high and impact angle is also high, then there may be melting. So if melting occurs, then of course this is a different type of wear, because molten metal will flow out and eventually it will solidify and come out. So that is a different type of wear. So we have discussed here 5 types of erosion mechanism, and depending on the type of mechanism, we have to prevent. So it is clear that the erosion mechanism depend on the angle of impact, type of material, and hardness of the impacting particle. So the relative hardness of the eroding particle and that of the surface is important. But in most cases, we cannot do much about it. So we can only do one thing, and that is give a hard coating or harden the surface so that the erosion can be lessened to some extent. In many cases, erosion is used as an advantage For example, erosion is used as abrasive machining. Erosion is used for abrasive cleaning, and many other usages are there. So erosion is not necessarily always detrimental. It may be useful also. Okay, now we go to corrosive wear. Now, corrosive wear is again a very broad topic and is a subject of research. But here we consider only very few points. That is, what is corrosion? Because what corrosion, when corrosion occurs and the corrosive product is removed, then only we have got corrosive wear. So we must understand the corrosion, what is corrosion. And we know that corrosion is a chemical or electrochemical reaction with the environment. Now, in the electrochemical reaction is a process caused by either or without accompanied by the passage of electric current. Not necessarily we have to have an electric current, but what is important here is the transfer of electrons between the two surfaces, one solid and one liquid. So this is basically electrochemical reaction. And the other one is oxidation. Oxidation is usually thought of as addition of oxygen, but that may not be so. Oxidation can occur when an atom or molecule or ion loses one or more electrons in a chemical reaction. So losing of electron is basically an oxidation. And that happens when oxygen is added. Say, for example, if we take a metal and acid, and then we have a salt. And this way, metal is taken away very slowly, but surely, over a long period of time, the metal is worn away. Take, for example, Fe plus 2HCl, FeCl2 plus H2. Here, Fe is oxidized and chlorine is reduced. Now, one important thing has been observed for ice engines and other corrosion, that there is a peak at a certain percentage of oxygen composition or oxygen percentage. The wear will slow down, but friction goes on increasing irrespective of the environment. Of course, in some cases, environment also will affect friction, but corrosive wear has a point of inflection. Now we look at corrosive wear in more detail. There are very many different types of corrosion. And depending on the type, we have to arrange the remedy. Say, oxide corrosion. As we discussed earlier, oxide corrosion is in general an electrochemical process in which metals are converted into the compounds such as oxides, or by interaction with corroding medium, which may be a lubricant or some other chemical, and oxygen and one of the metals loses electrons and the other one accepts it. Usually, the oxygen accepts the electrons, and the electrons are lost by the other component. So this type of corrosion occurs when, say, for example, in thermal power plant, Usually the pipes are lagged or protected. When the protective coating is gone, then this type of problem occurs. And in thermal, thermal power plant, this is a very big issue. Then, in some cases, this protective layer may be useful because when there's a protective layer, then for some time the surface cannot be corroded anymore. But depending on the load and the speed or some other atmospheric condition, if the protective layer is gone, then it will be corroded again and the process repeats itself. And then the corrosive wear rate is very rapid and more material will be lost. As I was saying, that the power plant problems, in power plant, this type of wear, corrosive wear is very prominent, and there usually pipes are lagged, and it usually happens during shutdown. Thermal power plants are normal. There's a scheduled shutdowns, and that is the time when the atmospheric water vapor comes in contact with the metals and corrosion starts. So there, we can have different types of corrosion there, such as galvanic, hot corrosion, stress corrosion, fatigue corrosion, etc. We'll look at some of these in a very brief manner. Galvanic corrosion. When two dissimilar metals come in contact in the presence of an electrolyte solution, then one of the metals acts as anode and the other as cathode. And the more reactive metal, or the metal with higher negative electrochemical potential, acts as anode, and the other one acts as cathode. In the presence of an electrolyte, ions migrate from anodic metal, leading to the rapid removal of anodic material. So this we sometimes is described as a sacrificial wear, because their anode is sacrificed and the cathode is protected. So galvanic erosion is a way of protecting one surface and at the cost of the other surface. Hot corrosion. This is an accelerated corrosion process where accelerated oxidation process in which metals are heated to temperatures say up to 900 to 700 to 900 degrees centigrade. And in the presence of sulfate deposits, which may be formed by the reaction of sodium chloride and sulfur compounds in the gas phase around the metal. So if we have a sulfate deposits, then this type of hot corrosion will take place and will corrode the surface in a very rapid manner. So there obviously the temperature is to be controlled if possible, or again coating or lagging, some kind of other measures have to be taken. Erosion, erosive corrosion. Now there are many components in thermal power plants or elsewhere where there are high-speed fluids, say pumps, valves, pipe fittings, and other such hydraulic components where there are high-velocity fluids. And these, of course, will clean the metal surface, and this causes the loss of base material. And once that happens, then the virgin metal will be exposed to corrosion again, and the aggravated corrosion will go on. So erosion is again a very detrimental process in corrosive wear. So in the presence of high-speed fluid, corrosive wear will be repeated and will lose metal more and more. Then there is stress corrosion cracking. In many cases, we see cracking on the surface. This is a combined effect of tensile stress and the corrosive environment. The stress may be applied, or it may be due to residual stress, such as welding and other. So when the stress corrosion is can also be defined as galvanic corrosion, because here the stress area of the metal acts as an anode and the unstressed area as cathode. So the stress corrosion material fail in brittle manner and can be very dangerous, because this kind of failure takes place without any prior notice. So unless we are careful, stress corrosion can certainly burst the pipes and lead to dangerous consequences. Then we have got fatigue corrosion. Now, this is again a combination of the influence of fluctuating stress and corrosive environment. So when we have got corrosion and a fluctuating stress, then the premature fracture would occur, and particularly in situations where corrosion pitting and other things occur. In some cases, fatigue strength of material may be lowered to take care of this type of corrosion. And the figure below shows two graphs. One is stress and the number of cycles, usually a single curve. Figure A shows without corrosion, and figure B or C shows with corrosion. So with corrosion, we can see that the endurance limit is lowered, and hence it is harmful. So there again, we have to, if we want to get rid of this type of wear, we have to choose material carefully. So prevention, again, prevention depends on the type of wear, but there are broadly few steps can be taken. One is, as I said, barrier coating or painting. These are probably one of the best ways of taking care of the corrosion. Painting plastic, such as epoxy, nylon, urethane, and other materials, other coatings will adhere to the surface to create a thin film, and this will act as a coating to protect the surface and protect the surface from electrochemical changes. Then use of alloys. In many cases, alloys stop corrosion. As we know, stainless steel is an anti-corrosive material. Like stainless steel, there are many other alloys that can be used for protecting materials or stop corrosion. Then galvanizing. Galvanizing is again a process of coating metal with thin layer of zinc. Now this again is a method of coating that will stop the corrosion or reduce the corrosion as long as the coating remains. So galvanizing is one of the ways of stopping corrosion. Then in many cases, we do greasing or oiling. Many components in the industry are greased and oiled, so that as long as grease and oil stay on the surface, the atmospheric water vapor cannot atmospheric oxygen cannot come into contact with the metal surface, and corrosion will be prevented. There is another important corrosion, which is called fretting corrosion. But again, all these are topics of very large scale research. This occurs when there is a small amplitude vibration and the removal of corrosion product because of the vibration. And as the corrosion product is removed, fresh surface is exposed, that will be corroded again, and the process will repeat. So in many cases, we cannot avoid the amplitude or vibration. So again, the choice of material here is important. And again, to some extent, coating may be helpful. So this is where we stop here, because it's a very broad topic, as I said, and many of these are topics of large-scale research today. So we stop here today, and we'll start a new topic next time.